Thank you so much. I hope you enjoy the conference so far. So yeah, I'm going to shift the topic a bit. We've been talking a lot about quantum computing and thermodynamics. I'm going to be talking about quantum communication. And I'm going to present a preliminary study on the conception of quantum communication. So I'm trying to answer some open questions that we have. What is the expected energetic cost of a quantum internet architecture? Can we expect any energetic advantage from quantum communication over classical communication? And to answer that, we have to look at how do resources scale with noise or with number of parties in communication protocol. So a small disclaimer, you won't find answers to this question in this talk. This is just a preliminary study, as I'm saying. But let's start by the beginning. Once upon a time, there was the classical internet. Internet stands for internetwork. I just learned that here. So it's a network of network with hybrid systems, satellites, servers, data centers. And the energetic cost of the classical internet is something that is quite hard to estimate, because just 1 minute on the internet represents a lot of different application, field, data center, and involve a lot of industry that don't necessarily give out their data on the energy that it requires to watch videos on YouTube or to go on Netflix. But if you Google a bit, you see that you find this type of graphs that shows that the main sources of energy consumption in the classical internet come from data centers because of the AC, blockchain, as we've been already talking about, the actual devices that are involved, that is going incrementally, is with the connected house and connected cities. The networking protocols, so all the protocols that are required to make the internet function, all the IP, TCP/IP architecture. And there is a future cost to be dealt with that comes here. You see like the red part that comes from AI, ChatGPT, and all this kind of stuff that is booming. So I found on the internet after some search that the consumption could reach 5 to 20% of the total energy consumption. But again, it's super hard to estimate right now. So let's go quantum. What is the quantum internet that I've been mentioning? So I'm defining the quantum internet as a global quantum network. So a quantum network is basically a graph where the nodes are quantum devices. And on top of the network, you need to have standardized protocol, as I said, like TCP/IP for the classical internet, that are used to route messages through the network, to do error correction, to display your message properly on the application. And if you have both of them, you have something that you call a quantum internet. So it's again a network of networks, as you can see in this small image. I will go a bit more in detail of this image later. But yeah, you see there are small networks connected with backbone nodes. And the general goal for a quantum internet architecture is to generate entanglements between two or more parties. Once you have entanglement, you can do all sorts of cool applications. And I just want to say that the quantum internet is not here to replace the classical internet. It might seem obvious, but it has an impact on the energy cost, which is that you have to add the cost of the quantum stuff on top of the classical internet. So before I go into the energetics, let me just motivate why do we want a quantum internet. We have tons of applications already that we started talking about. The first one is obviously QKD and the multipartite counterpart conference key agreement. So this has influence in authentication, in communication security, privacy preserving analytics, and this kind of things. Distributed randomness generation. This will help us do online gaming, online gambling, and a lot of cool games. Enhancement in cryptography primitives like bit commitments, Byzantine agreements, leader election, all these kind of things can be enhanced using quantum networks. Clock synchronization is a big thing, together with enhanced measurement that we've also mentioned before. This is applications of quantum networks. My personal favorite, blind and private delegated computation. This one could lead to a big shift in energy consumption, actually, because with this application, you can use a machine that is not yours, completely privately and blindly. So you could use an Amazon server without Amazon knowing what you're doing or why you're using the machine for. So it means that theoretically we could have one quantum computer somewhere in the city that everyone could use securely with just single photons. This could lead to a shift of paradigm. We don't need to each have a quantum computer at home. We can all use the same one or two or three, which also is a gain in energy. So there are many more applications to be discovered, and if you want to know a bit how this works and how they are implemented, there is a cool wiki-like website called the Quantum Protocol Zoo, where everything is detailed. So what about the energy? What is the energy cost of a quantum internet? So in order to derive the energy of something that doesn't exist yet, we need to first build a model of what it could look like and then estimate what it is. So this is schematics from works from my PhD, where you see a network with, as I said, the backbone nodes that link small networks that are supposed to be quantum cities, network within a city. This is long-distance communication nodes. We expect them to be quantum repeaters or free space communication on the ground or using satellites. The energetics of these I have not studied yet, but in the future I plan to go there. So now I'm still focusing on local protocols that you can perform within a city. And we start here by analyzing building block protocols, the basic of communication. And the most basic protocol that we know is quantum key distribution. So let's go a bit more into the detail of QKD, and let's see what impacts the energy cost of quantum communication protocol. Of course, there is the hardware. What's nice about communication is that we already more or less know that it will be photonics and that it will consist of sources and detectors, and we already kind of know which hardware is going to be involved, even in the end phase. So we have sources consisting of either weak coherent state sources or SPDC sources. The detectors will be most probably SNSPDs, but SNSPD, so supraconducting nano something detector. Yeah, I'm not an experimentalist. But they involve a lot of cryogenics, and they are costly, as we will see. You have other electronic devices that are involved, and you have fiber or free space. So this is the hardware part. Also, for one functionality, so for one thing that you can do, sometimes you have different protocol achieving it. Different protocol involve different hardware, so different energy cost. For example, for QKD, you have many different protocols that do the same thing, which is sharing a key. BBHE4, entanglement-based QKD, MJ QKD, CV QKD, all of them have different hardware, and this impacts the energetic cost. You can choose different encoding for the information in your photon. This also influences the energetic cost. And of course, on top of that, you have a classical cost. In the case of QKD, you have to do some error correction, some privacy amplification, and this, depending on the level of security that you want to achieve, costs more or less. So let's see how much it costs. The method that we use is basically to sum the energy cost of each of these devices that I'm mentioning. So you sum the number of sources, plus the number of detectors, plus the number of fusion stations. So this is what you use to create a state from the lasers and sources, plus everything else that you might choose, quantum memories, motorized wave plates, or whatever. And on top of that, you have to add the classical cost. So it's not clear for us yet if it's something that you add at the end or that you multiply with everything. It depends on the protocol, it depends on the application. But to have some benchmarks, and as it was said just before, to create a baseline of what it could cost, we use the MNR framework presented by Alexia in her seminal paper. So we fix a metric and we vary the noise and the resources to see how it's cost. So in the case of BBHE4, I guess you know it, but just in case, BBHE4 consists of Alice sending photon to Bob's. And if you want to understand the conception of that, you have to closely look at what happens when you do that. So you have a source sending photons up to the detector, and you have some sources of losses. So the brightness of the source will give you a probability that the photon is actually created or not, given by p qubits. Then the photon has to enter a fiber with some probability, p coupling. The photon has to go through the fiber, which this probability depends on the distance, the transmissivity. And then it has to be detected. On top of that, you have some errors, some probability that the qubit is flipped. So I want to create a 0 state and I get to 1 for some reason. This happened with some probability. Usually when you look at BBHE4 or QKD in general, you look at the channel efficiency, so the number of click at Bob's detector over the number of photons that was sent. And you look at the secret key rate. So for now, I'm focusing on the asymptotic secret key rate. I'm not so much looking at error correction and privacy amplification type of problem, but we are studying it. And this is given by this formula. So the figures of merit of QKD are, we will look how much energy it takes to get 1 gigabyte of secret key. We will vary the noise, and we will vary the different hardware involved, the encoding, the resources. So the formula that I was showing here, in the case of BBHE4, reduces to 1 source plus 1 detector plus the classical cost. It's way more simple. So if you want to know what it is, you go to the lab, you go to C Pascal that is there, and that provided me with this cool table of different lasers, different detectors, and everything that is around it in the case of QKD. And it will give us, he gave me the power that it takes to manipulate them, and I just draw your attention to this SNSPD that requires cryo. So cryogenics needs a lot of time for cooling. We chose to take 24 hours because, yeah, some of them are longer, some of them are shorter. But once you have this, you can start estimating energetic cost by just summing everything and see how it gets. So we looked at some common setups. The first one is the setup with weak coherent states using a laser and SNSPDs. And then we varied the frequency used, the type of source, and the detector that is used. We chose a detector that is way less energy costly. And we simulated how much time it takes to get 100 gigabit of secret key for each of this setup. And this is what we got. So you can see the four different setups that I presented, the energy that it takes to generate 1 gigabyte of secret key as a function of the distance. You see several interesting stuff. This curve here goes very fast, very high, because we operate at 780 nanometers, and the photon get lost in the fiber really quickly. So it costs a lot of energy really fast to get 100 gigabit of secret key. But more interestingly, you see a sweet spot here. So I'm going to be honest, I've played a bit with the parameters to get the sweet spot. This is preliminary results. But you can see that using APD detector that are less efficient, but less energy costly, can give you the same result as using SNSPDs in more time, but using less energy. So you might have an energetic advantage of using APD over SNSPDs in some distances, and then it would be better to use an SNSPD. So this is not definite numbers, but it shows that it's interesting to look precisely at the hardware that you use to see which one is the more energy efficient for the parameters that you have. Then using one setup, you can also vary the noise, so the QBER in this case, and then you see without surprise that the more QBER you have, the more time it takes to get the same number of secret keys, so the more energy it takes. You can look at different protocols. So very simply also, if you compare BBHE4 with entanglement-based QKD, BBHE4 consists in one source and one detector, while entanglement-based QKD consists in one source and two detectors. So you obviously have a different scaling of the energy. So yeah, that's what I said in the beginning. Different protocols involve different hardware. And so it is known that entanglement-based QKD requires less trust in the node than BBHE4. So here in the specific case of QKD, there is a trade-off between the trust and the energetic cost of your protocol. You can also have fun varying the encoding. So this is MDI QKD, measurement device independent QKD, using polarization encoding or time being encoding. And you have slight differences in the hardware involved, and you can see that for time being, you use intensity modulator, for example. These have a small cost in energy, so if you want to optimize as much as you want the energetic cost, you also have to pay attention at this kind of stuff, because little differences in hardware can lead to big differences when we scale up. The choice of encoding can also change the rate that you have at the end, but this is quite hard to actually simulate and estimate, so I don't have numbers to show. But yeah, it's worth mentioning. Now, internet is interesting if you do multipartite stuff, not only QKD, right? So multipartite stuff, right now they mostly consist in generating multipartite entanglement using this state, the GHZ state. You have a number of protocols that you can do with a GHZ state. So you have a GHZ source. But the problem with the GHZ state is that the way we create it right now in the lab is by using SPDC sources and mixing them with a beam splitter here. So this is called a fusion. So from two Bell states, you get a GHZ4. And if you want to increase the number of qubits, you have to add a source, and so on and so forth. And creating a state is probabilistic, the fusion is probabilistic, so the more you want to increase the number of qubits, the more energy you have to spend, and it scales exponentially. So here is a log scale, and you see that it just grows with the number of qubits. So GHZ creation is not scalable at the current state. So there are protocols like conference key agreement where we are looking at what if it's better to use Bell pair sources and to go from bipartite entanglement instead of using GHZ set source. Probably, again, there is a sweet spot between using one over the other as the number of parties grow. So as a conclusion, I presented the preliminary results of our work with Federico, Paul, and Pascal that are here. That is a hardware-dependent study of the energetic consumption of basic building block network protocols. We focused on QKD and genuine multipartite entanglement creation. But I also started some other projects in the same field, energetic of CVQKD with Carlos Pascual. We're trying also to look at some more fundamental energetic cost that depends on the security parameter that you want to achieve. In the future, I want to look at energetic of long-distance communication and completely characterize the quantum internet, have an idea of the full cost of the quantum internet. So if anyone is interested in working in that, please contact me, we can work together. And I would be super interested to do that. And with that, I thank you, and please don't forget to subscribe to the QEI mailing list and the YouTube channel.
Thank you very much, Raja. Is there someone who has a question about the energy cost? My microphone is not working.
There is somewhere.
Yeah, so of course, I always want, there's two kinds of questions. There's either to understand better or to want more. So this question is one of wanting more. So I'm very interested in where things are with quantum repeaters and whether, so actually maybe in something you did, what's the maximum distance? So you assume no quantum repeaters, right?
Yeah.
And so what's the maximum distance you can go to without quantum repeaters with a reasonable
It's approximately 150 kilometers. It depends on what type of source you use, of course. But then there is a distance where the dark counts of the detector prevail over the number of clicks that you get. So yeah, 100 kilometers, let's say.
So do you think quantum repeaters could bring the cost down, or will make them explode? I mean, if you seek maybe for the same distance, for 150 kilometers.
Yeah. So quantum repeaters will involve quantum memories. So there will be no quantum repeater before we have quantum memories. And quantum memories will have to operate at low temperature, probably. So this will bring the energy cost up, for sure. Yeah, if you look at satellite communication, it's a bit less obvious because the satellite in itself doesn't cost much to operate once it's in the sky, but there's a lot of energy required to send it to space. So yeah, quantum repeaters are definitely something that I want to study. There are different ways of thinking of quantum repeaters. There are even photonic quantum repeaters that may be more energy efficient. So yeah, future work.
Okay, I see another hand back there.
Hi, yeah, just a small question to clarify. At some point you said that we could be all sharing one single quantum computer to do it, etc. But isn't it already what we're doing with the usual internet? You seem to present that as what would be a new feature of the quantum internet network, but
So there exists cloud computing right now, but it's not what we use. We all have a classical computer at home, right? When I perform a simulation, I do it on my computer. And then if it's a hard simulation, I use a supercomputer or something like that.
Yeah.
But this is not secure, and this is not blind. So right now what happens is that I'm using someone's computer that is more powerful, but he has access to all of my data. With Quantum, you can do that completely privately.
Okay.
And you can check that the answer that he gives you is the right one. There are very interesting protocols. If you want to know more about that, I can
Okay,
give you references. But
Sure, but then that's related back to encryption using quantum technologies.
it's more than encryption. It's really it's the same idea, but it's more than encryption. It's not like you encode your data and you send it. It's you, if I remember correctly, you send your data in a way that it's impossible for the person to know why you send this data or what this data will be used for.
Okay, but I think the Tor network already works like that, no? Or maybe we
Maybe.
maybe we can talk about that later.
Maybe.
Then. Okay, thanks.
Okay. Are there any other questions? So I have one. So people have told me that they like it when I ask ethics questions, so I have an ethics question for you.
Yes.
So in the beginning you said at some point that in the quantum internet, if you want to make this global, at some point we will have to operate satellites,
Yeah.
probably, and that makes, from a quantum point of view, a lot of sense. So I just looked it up, like a rocket launch consumes around 1 ton of, like it emits 1 ton of CO2 per second, roughly.
Yeah.
So to give you an idea, my flight from Paris to Singapore is back and forth 6 tons, roughly, I guess. So we are, like, this is a lot of CO2 to send up your satellite. You probably need several. And so on. Like, I'm kind of wondering, I'm sure you don't have an answer to this, or a kind of, there is no right or wrong answer, but like, from what point on would this cost kind of be worth it somehow?
Yeah, so I mean, this is an interesting question. I'm gonna go in your sense. I don't like satellite either. For another reason is that satellites are also only available for a few minutes. They have to, they move in the sky, and if you use geostationary satellite, they are too far. So you cannot use geostationary satellite to do quantum communication. So yeah, I'm actually studying alternative to satellite, namely balloons or drones. That would work, but this doesn't work over oceans. So for communicating from Paris to New York, for example, you kind of need a satellite, unfortunately, I would say. But I agree with you, this might be the more costly, although there is a trade-off, right? Because once it's in the sky, it doesn't cost much. So maybe if we manage to make a small satellite that can last long, it will cost less than using a balloon that you have to replace every 6 months or something like that. So yeah, I don't have an answer, but I actually agree with you. Satellites are not the right way to go if you think energetically speaking. Yeah.
So then, of course, if someone knows a quantum way of getting a satellite up in the air that doesn't involve rockets, you know what to do. Any other questions? No, I don't see any hands. If not, then I think we can close the talk, the session, and the day. So let's just thank basically everyone who gave a talk today.